Right, our next talk is towards quantum multi-party session types. It's given by Vikraman Choudhury.
Okay. Hi, hello. I'm Vikraman from the University of Bologna, and this is joint work with Ivan Lanese and Ugo del Lago, who's also here. So I'm going to tell you about session types and what they might do for quantum protocols. This is a paper which was published last year, and I'm presenting an overview of what we have in the paper. Okay. So since it's about quantum session types, but this community is for quantum, it would probably be best to start with a brief introduction to session types. So session types are they were introduced about 30 years ago, and they're a formalism for specifying communication protocols. And there are two important aspects behind this typing discipline. So you get to say what is the type of data that you're exchanging between processes and in which direction data is flowing. Okay, so and the purpose of having a type system is to guarantee some safety properties for your programs or processes, right? And one of the most important properties that session types give you is that once you type check your processes, it's guaranteed to be deadlock free. Okay, so none of the processes get stuck during communication. And then there are also lots of other properties like session fidelity and such. I'll not go into the details of these. And session types are normally used for typing process calculi, so starting from the pi calculus and different variants of the pi calculus. And they've also been successfully used to type other functional object-oriented languages, actors, and many other kinds of programming languages. A short history of so session types were introduced in 1993 by Honda, and it's types for dyadic interaction, so going both ways, right? And an important logical discovery was that session types give you a Curry-Howard correspondence between linear logic and processes. So there's this program by Samson Abramsky called Proofs as Processes, and it was shown in 2010 that you can find a correspondence between intuitionistic linear logic and intuitionistic session types, or you can also have classical linear logic and session types, as in Phil Wadler's CP calculus. Okay, and probably the most important shortcoming of session types is that they're always binary, so you have always a sender and receiver. And multi-party session types extend these to multiple processes interacting in a distributed system. So Popple 2008 was about multi-party asynchronous session types. Okay, I'll try to give you a simple example of typing using session types. So this is a simple server and client. The server has this type, and the type starts with an ampersand symbol, which says that the server is going to offer three different choices. There are names for these choices. These are called labels, and they are disjoint sets of names. And then there are these type constructors, question mark and bang. So the question mark says the server is expecting to receive an integer. So when you take the first branch to add two numbers, you expect two integers as input. So the server will receive two integers on the channel, and then it will return an integer. So that's the bang. Then every int has a dot at the end, which stands for sequencing. So everything happens from left to right, right? The communication goes in a linear way. And when these operations end, the server will continue as S. So there's also an implicit recursion happening here. Okay, so there are three branches. There is addition, and if the server offers a negation choice, if you take that branch, the server expects to receive an integer, return an integer, then continue. And the protocol ends if you take the quit branch, which is indicated by an end. Okay, dual to the server, there's a client. The client also has a session type. So when it's the client, there's a choice between which three branches it could take. But each branch has just exactly the dual of the server's session type. So the bang means that the client is going to send an integer, then receive an integer from the client, from the server, then continue. Okay. So there's a so these are the types, right? And then there are you have to write programs which type check with the signature. So there are different term languages for session types that I mentioned, but I'm not interested in going into details of these. But when you type check, you have to make sure that the client and the server are always dual, so that there is one channel between the client and the server. And there's a bit of an unfortunate clash of connectives between linear logic and session types. So the bang really doesn't mean the linear logic exponential. If you're confused about that, I understand. Yes. So session types give us all these different connectives. So and means external choice. The O plus means internal choice, and then the question mark and the bang for input and output sequencing, and then there are these things called choice labels, which are disjoint finite sets and end of protocol. Okay, now I showed you duality between client and server, but when you have multiple sessions in a distributed system, you can have pairwise independent protocols that you can type using binary session types. But if you want to type the whole system, you want to order interactions in 2 different protocols. So binary session types cannot do this. So then we get to multi-party session types. So multi-party session types have 2 different kinds of typing. There's a global type, which describes the whole system and what kinds of interactions are happening between all participants. And it gives you a mechanism to project the global type onto a participant using a projection function. And when you do that, you notice that you only have interactions between a local participant and the rest of the system, which is like a binary session type. So when you stratify the typing, you can actually get local type checking using binary session types and recover the theory of communication safety for the original binary session types. So rather than explaining classical multi-party session types, I'll just show you how multi-party session types can be adapted for quantum protocols. So there were the previous talks, introduced quantum protocols. So you have a quantum network or a system which exchanges both classical and quantum information. You can have quantum or classical data. You can have quantum or classical channels. And obviously, you have to make sure that you have the quantum effects like measurement and so on. And there are lots of quantum protocols in the literature. There's even a quantum protocol zoo, which is a wiki that collects all kinds of descriptions of quantum protocols. Okay. I think there are plenty of languages which describe quantum computation, like quantum circuits and quantum lambda calculus, and then there are practical languages based on that. But when it comes to quantum protocols, we don't really have a lot of quantum process calculi. Okay. So I want to point out the 3 important ones that I know of. So POPL 2005, there was communicating quantum processes, or CQP. And then 2009, there was the classical CCS, communicating systems, but done for quantum. And then POPL 24, there was quantum bisimilarity by extending QCCS with linearity. Okay. So in this talk, we're going to go towards session types. So none of these languages are typed. These have simple types for the quantum data, but nothing that guarantees communication safety. Okay. So to give you an example of what our system can do, let me start with quantum teleportation. Right. So I think you all know that it's a way of using a classical channel and entanglement to transfer quantum information from sender to receiver. And if you go to the Wikipedia page, it's normally described informally in text, or using diagrams like this, where you read, the diagram from left to right, going forwards in time. If you go to the work on categorical quantum mechanics, it's explained using a string diagram. This is also great. But I want to describe this using the pi calculus. Okay, so first let me just informally read this string diagram. So there are 2 participants, Alice and Bob. Okay, and there's a source which gives you entangled pair of qubits. So the first step, Alice owns a qubit Q, and Alice wants to teleport this to Bob. So the source generates an entangled pair of qubits, X and Y, sends X to Alice and Y to Bob. Alice does some quantum operations on Q and X, Okay, so first it does a controlled NOT, then it does a header mard on Q, measures Q and X, and it gets 2 classical bits, R. And now Alice and Bob share a classical channel, so they're allowed to exchange classical data. So Alice sends these 2 classical bits to Bob. And then Bob does a Pauli transformation using R and applies it to the qubit Y that Bob owns, and then continues the protocol. Okay, so these are the 5 most important steps, right? So let's. I'll write down a session type which explains what's happening in this protocol. Okay, so so the first step in multi-party session types is to write a global type which describes the whole system. So what do we have in this system? We have an environment which tells you, okay, this process has some kind of input, the qubit that it wants to share, and there's an output, which is what happens after the protocol ends. Okay, so we use a participant env to model input and output. We use a source, which is going to send quantum bits, references to quantum bits to Alice and Bob, and then we have the 2 main participants, Alice and Bob. Okay, so for this system, we write a global type. So the global type goes like this. So it's a sequence of operations. So the first step is the environment sends a qubit to Alice, written like this. Then the source sends a qubit to Alice and a qubit to Bob. And then Alice sends 2 classical bits to Bob, and then Bob, that's the output that Bob has, so it goes to inf. Okay, and then the protocol ends. So this is the global type of the system. Then the next step is to look at the local type. So given this global type, the multi-party typing system gives you a projection function that you can use to compute the projection for each participant. So if you project this G global type onto Alice, you go through this recursive structure and see what are the interactions that Alice has. Okay, so the first interaction is well, Alice is expecting to receive a qubit from env, so that's the AND, like the server, right? Then Alice is expecting a qubit from source. Okay. Then Alice offers 2 classical bits to Bob, and that's the end of the protocol. So this is a binary session type when you project out. Okay, you do the same thing for all the other participants, and you get 4 different local types for each, for each participant, right? Okay, and then what you do is you have to write the programs which will type check with these types. So when you write a multi-party system, you write a process in your process calculus. You write 4 different processes for each participant, and you tag the role of the participant. So Alice is the name of the participant, and Alice is played by this process PA and Bob, and you compose them in parallel. Okay, so so here's a term calculus that we provide for writing processes, and this term calculus takes the primitives from the pi calculus for sending and receiving, which are common in session types, and extends them with quantum primitives. So you have ways to create new qubits, you have ways to perform unitary operations, and you can do measurements. So just to describe the quantum teleportation protocol for Alice, so the AND is exactly the same as the type, but now you bind the received qubit to Q, then continue by receiving X from the source, do the C0, do the header mard, and all that, and finally end the protocol with the 0. So 0 is the empty process, which ends the protocol. Okay, so these are the terms for the processes for each participant. There are a few important issues around alpha renaming and maintaining the variables and references for qubits, and we have to be careful about maintaining linearity when writing these things. So that's what the type system is going to give you. The point of the type system is to type check all of the multi-party system, which is M, with this global type G, and the typing rules will guarantee that the system is safe. So I have to tell you a little bit about the type system, what it is. So this is a lot of syntax, but let me maybe point out some of the important things. So what we have is a syntax for global types, and a way to do recursion on global types, because processes are long-running programs. And then the usual session type primitives for external choice and internal choice, along with recursion and all this. And then the basic types are your classical data and bits and qubits. Now qubits have to be treated special because we want to make sure they're linear. Because they cannot be cloned or deleted. So, so the syntax for expressions and processes now has operations for classical data and operations for quantum data. So just to highlight a few things, you can you have send and receive primitives. You have primitives for doing recursion and process definitions. And you also have conditionals, but the conditionals are only allowed to branch on classical Booleans, okay? And then the multi-party system takes the participant name and the process and tags these things. Okay. Now, there are lots of typing rules to type check the system, but I want to point out that this adding linearity to classical multi-party session types makes things a little bit complicated. So, for example, the usual typing rules, which keep one context around, now has to be split into a dual context, so which is very standard in type theory. So you have to add recursion and linearity, you have to maintain separate environments for recursive variables, classical variables, and quantum variables. And on the right, you have the terms for processes and the session type, which tells you what the protocol is. And to point out a few highlights, we take the classical multi-party session types and add linearity for quantum data, recursive types, and processes and expressions for quantum computation and communication. Okay. These programs also have semantics. So we give a semantics in terms of a labeled transition system. So the configurations of the LTS are a pair of things. So the quantum register, which keeps track of the quantum references and the data that they have, and the multi-party system M, which is the term of processes. And these transitions are non-deterministic and probabilistic. And then we have to extend the multi-party communication rules with rules for quantum computation. So just to point out, for example, when you do measurements, you have to project out and get the probability, and this probability is used to do a transition to the next process. And all this. Okay. So this semantics is this type theory has good meta-theoretic properties. So to informally tell you what the results that we have. So the basic things are subject reductions. So transitions, when you do a transition, you have to keep the type, so they preserve typability. And when you do session types, the global type and the multi-party system, the processes, they evolve at the same time. So when you are going and type checking, the type evolves and the process evolves, and both of them have to be in bisimulation. So that's session fidelity. There's obviously progress and type safety. So if you have a well-typed multi-party system, it's going to keep reducing until it stops the protocol at end. And in addition to classical communication safety results, we also have some results about qubit safety. So because of the linearity of the system, you can guarantee that every qubit reference is exactly owned by a single process in the system. And there's a sort of adequacy between the typing environment used for type checking and the runtime qubit environment, and they match up. Okay, so these are the results. And I want to conclude by saying that we have a type theory for writing quantum protocols. There are some nice meta-theoretic results. We have, I showed you teleportation, but we have done it for other, we have used the type theory to type check other quantum protocols like secret sharing, bit commitment, key distribution. You can read the extended technical report on arXiv. And maybe the second thing I want to say is the reason I'm calling it towards quantum multi-party session types is because it's all very preliminary as a type theory, because it skips a lot of important features of session types like session delegation and multiple channels. and it cannot do quantum channels either. We're only typing with classical channels. And there's more to be figured out, like writing a type-checking algorithm and doing type inference. And also, all of this is very syntactic work, and I don't know connections to the other denotational models of quantum protocols. So that's something that I'd be happy to talk to people about. Thank you.
Thank you for the nice talk. From your talk, I understood the main difference between like usual multi-party session type is that linearity, and but linearity is not only for quantum computation, but for example, like if you have a huge data you don't want to copy, you also want to like keep it linear or applying. And can you? My question is that like, can you do a like similar story for that kind of
So
thing?
the system was done like for a general linear type, how you can do it, and then just because we add the primitives, the typing rules have to be specialized to quantum.
Right.
Or otherwise, the system works for linear, any kind of linear system. Yes.
Right. Thank you.
Hi. The global type you showed for quantum teleportation does, if I understand correctly, show that Bob will return a qubit to the environment. Does it also check that Bob, in fact, returns the same qubit that Alice originally got? And if not, you know, what kind of work would be necessary to check that property?
No, it does, because this Q:qubit, because it's the same Q that Alice receives and Bob returns to the environment. So that guarantees that it's the same qubit, That's an important point, yes.
So when you say it's the same qubit, it literally means like, you know, the
it's
qubit
a reference.
ket is equal to ket at the end.
Right? So, I mean, you can look at this from the operational semantics. So whatever Q was pointing to before the communication started is going to be the same Q afterwards. So the operation, the subject reduction plus the typing rule proves that it's the same qubit.
Okay, thanks.
Actually verify that you looked at the identity function.
No, we don't actually do that. Yes, that's right. Yes. Whether it's the identity function on the same queue.
Yeah, I had a similar follow-up.
Okay.
Can you read off the type that is going to be the same qubit?
Yes, it's the same qubit reference because it's an operational semantics. But I can't extract a function on the qubit register out of this. Not yet, until I have a denotational model or something. Yes.
Right. So one could imagine trying to do a logical relation to.
Sure. Yes.
All very nice. You talked about ownership towards the end, that you have a theorem about ownership of the qubits.
Yeah.
What if a qubit is entangled across two processes? How is that going to work?
If a qubit is entangled, so for example,
I meant to say a pair of qubits is entangled. I'm sorry, I meant to say if a pair of qubits is entangled across two processes, so one process kind of has one of the qubits and the other one has the other one, but they're entangled. Is that affecting your?
No, that's so. For example, this is the type of PS. So XS and YS are entangled, but the references are different.
The references are different.
Yes.
Thank you. Let's thank our speaker again.